Hey, what's up guys? It's Dr. D-Flo back with part 3 of the large format 3D printer build. In this video, I'm going to put together the electrical cabinet, attach the massive Keenovo heater to the build plate, sort out the bed leveling, and then we should be ready for some test prints. Let's get started.
Dr. D-Flo.
Before we get to the electrical cabinet, I want to add some more limit switches. The original plan was to have 2 limit switches. One on the left side of the x-axis and one on the front left of the y-axis. The z-axis would be homed by touching off a tool setter such as this one. But when I've been turning the printer off, I've noticed that the gantry will sag if the pellet extruder is not moved to a central location before the z-axis motors de-energize. I can press on this screw and you can see it's moving. Those Teflon nut blocks that I machined in the last video have very little friction, and if the 20 pounds of the pellet extruder is too close to one corner of the printer, the nearest screw will start to turn, dropping the carriage. On power up, the gantry is all twisted, so I decided to install a limit switch at the top of each of the 4 z-axis columns. On startup, the printer will touch off each z-axis carriage individually, auto-squaring the gantry. I'm also using a second limit switch for the right y-axis to keep both carriages lined up. After the auto squaring is complete, this will be a nice starting point for the quad gantry leveling. Now is a good time to connect the wires coming out of the drag chain to the print head. I want to have the ability to disconnect everything down the line without having to cut wires. It's unlikely, but I might want to swap the pellet head out for another tool such as a router. I actually ran quite a few extra wires if I ever wanted to attach a filament extruder such as the E3D Volcano alongside the pellet head. To make these reversible connections, I went with military-grade Amphenol cylindrical connectors. These are intense. There's a very tight lock between the female and male ends. They're also rated for extreme environments, including high heat. I machined a right angle bracket that mounts right above the cable chain to hold all 4 variants of the Amphenol connector. The bracket turned out nice, but I accidentally snapped a tap in one of the 4 holes, so the big 10-pin connector will only have 3 bolts. In addition to the 10-pin, I also went with a 4, 3, and 2-pin connectors. The 2-pin is for the quad gantry probe, the 3-pin is for a blower fan for part cooling, more on these later, the 4-pin is for an extra stepper motor, say if I wanted that Volcano extruder, and the 10-pin is for everything else. The pellet extruder's heating elements, fans, thermistor, and ground connection. These pins are good for about 15 amps, so it will have no problem handling the heating elements. So here is my second attempt at purchasing an electrical cabinet. It's a couple inches larger in all dimensions compared to the first one, but I was trying to keep the cabinet as small as possible because I want to mount it on the frame of the printer. These cabinets are made out of steel and are incredibly durable, but also heavy. I did a quick test layout with all the electrical components, and again, I think that this box, even though it's bigger than my first one, is still on the smaller side. I wasn't able to use as many cable raceways as I would have liked, so this whole wire management is going to be a bit messy, but I think you're used to that if you've seen my other videos. I'm going to move this out of the way, and then we can go over all of the electrical components. This cabinet is going to handle 2 different voltages for the power, a 220 volt for the bed and a 110 volt for everything else. Both these circuits will be turned on and off by this large disconnect switch that has 2 separate poles for the 2 AC power lines. After the switch, the 220 volt and 110 volt lines both go to a separate set of circuit breakers and then contactors. The circuit breakers, of course, will switch off the power circuit if too much current is drawn. I'm most worried about the heated bed because I'm thinking it's going to draw an astronomical amount of current, especially when it first starts to heat up. But more on this later. After that circuit breaker, we have what I said were contactors, If you're not familiar with contactors, they are basically relays for switching high currents. An emergency stop button will control whether the contactors are open or closed, which will allow me to quickly shut down the printer if anything goes wrong. In series with the emergency stop button is this thermal fuse that I will place inside of the heated chamber of the printer. If this gets too hot, say if a fire broke out or if we had a runaway heated bed, this thermal fuse would disconnect that circuit which is energizing the coils of the contactor, effectively shutting off the printer. From the contactor, the 220 volt power will go to this solid state relay. This is responsible for switching on and off the voltage going to the heated bed. You can see just how big this heat sink is because it's going to be switching a lot of current. I had originally purchased a dual channel relay to switch both the hot wires at the same time, which would have been the safest route, but it never arrived. I could use 2 SSRs, but this just seemed overkill. I will definitely have the bed grounded, but let me know in the comments below if I should be more worried about switching 220 volt mains with only 1 SSR. But that is it for the 220 volt circuit. The live and neutral from the 110 volt circuit leave the contactor and supply power to these various regulated power supplies. These are 24 volt Meanwhile power supplies that are for the controller boards, which send power to the stepper motors. We have the servo motor power supply, and then we've got a 5 volt and 12 volt DIN rail power supplies for LEDs and other accessories. The 110 volt AC also goes to another solid state relay for powering the extruder's heating elements. I should mention that it would have been possible to power all the electrical components from 220 volts, but with this setup I can run the printer with just 110 if I don't need the heated bed. Now it's time to zoom in on the brains of the operation. This is the Duet 3 6HC mainboard. It is the latest product from Duet 3D, and I struggle to call this a 3D printer controller board because it's so much more than that. To illustrate my point, let's take a look at the Duet 2 Wi-Fi, which is the board I use in almost all my 3D printer builds. Here we can see labels for the X, Y, and Z stepper motors, as well as extruder 0 and extruder 1. There are also dedicated pins for reading the extruder and bed temperatures. If we look at the Duet 3, there is no indication that this board is for 3D printing. The stepper driver outputs are labeled drive 1, drive 2, drive 3, and the rest of the pins are labeled I/O except for these 4 dedicated temperature probe inputs. My point is that the Duet 3 was not created to be a board for just controlling 3D printers. It was designed to be a flexible platform for controlling nearly any multi-axis CNC machine. Along this philosophy, the Duet 3 uses trinamic stepper drivers that can support up to 6.3 amps peak current. This board has no problem powering OpenBuild's high torque stepper motors that I've used for the large format 3D printer. The one issue is that the large format printer has 7 stepper motors and a servo motor on the pellet extruder that needs to be controlled. The main board only has 6 stepper drivers on it. Fortunately, the capabilities of this board can be expanded by adding the optional 3HC board with a CAN connection over RJ11 telephone wire. In addition to 3 extra stepper drivers, this 3HC expansion board adds another 9 PWM outputs, 6 I/O ports, and 3 temperature inputs. You can just keep daisy chaining these expansion boards together to add more and more functionality to your build. The Technic servo motor only requires a step and direction signal, which is made readily available by this 1XD expansion board. All this flexibility is great, but it comes at a cost. The motherboard and 2 separate expansion boards altogether are over $400. Oh, and I forgot to mention, in order to get Wi-Fi on this printer, you have to connect a single board computer, such as a Raspberry Pi, which gets us even closer to $1,000 for this setup. This sounds very expensive when you compare the Duet 3 with other 3D printer controller boards, but when you compare it to industrial CNC controllers, this is in fact very affordable, especially for my application. However, it's unlikely that you will see me using this board for a normal 3D printer build. I'll probably stick with the Duet 2. I need to attach all the electrical components to the cabinet's backplate. For the power supplies, I will bolt them directly to it, but for everything else, I will use DIN rail. Most standard components, such as the contactors, fuse, solid state relays, can be directly attached to the 35mm rail. But for non-standard components like the Duet 3, that's not possible. So what I like to do is to take a solid state relay mount and 3D print an adapter which bolts onto this DIN rail mount. And then here we have the standoffs for the controller board. I will include a link in the description for these printable models. Okay, I'm gonna mount all these components and drill a couple holes in the electrical cabinet. I'll catch back up with you in a second. All the components are now wired to power. You can see how tightly everything is packed. For passive cooling of the cabinet, the power supplies need enough room to breathe. Obviously, I did not have enough space for this, so I went ahead and installed an intake fan and an exhaust fan. Both fans feature a custom laser cut grill. I also cut a hole in the top of the cabinet for a light stack. This is a dangerous machine. It's basically a glorified oven with a lot of pinch points. The red light will turn on when the bed or extruder reaches a certain temperature. The green light will illuminate when the printer is cool. Next, I need to bring the wires from all the motors, sensors, and heaters into the electrical cabinet. This will be accomplished through aviation connectors. These will allow me to disconnect components and remove the cabinet to service if needed. These connectors are good for about 5 amps, so I will use cable glands, like this one, in order to bring in the wires for the heated bed or power for the servo motor. The heater for the pellet extruder draws a little under 4 amps, so I will use a 2-pin aviation connector for that as well. The panel mount portion of the aviation connector will run through a hole in this metal insert. I laser engraved the position of the connector as well as a label for keeping me organized. You can see just how many connections that I will have to make. In preparation of mounting the cabinet to the side of the printer, I added 2 pieces of aluminum extrusion for support. I machined a couple brackets to bolt the corners of the cabinet to the extrusion. I will have to take the cabinet off to add the side panels, but for the calibration prints and filming purposes, it will be better to have those panels off for now. Even though the printer is massive, For some reason, the cabinet looks a little too big to be hanging off the side. I went ahead and added one more piece of aluminum extrusion just to make sure the side does not sag. Next, I need to solder the other end of the aviation connectors to the wires coming out of the drag chain. Electrical wiring is just tedious. Let's hope that all that work doesn't lead me to frying my Duet 3 boards. I wired up a temporary emergency stop button to close the contactors. All I need to do is to turn this switch on the side, and fingers crossed, there's no magic smoke. Fantastic. The LEDs on the power supplies as well as the Duet boards are all on. I don't smell anything burning. That's a relief. Next, I'm going to set up the Duet configuration file, which will allow me to home all the axes, getting the gantry out of the way for installation of the heated bed. So you just saw the printer home, but what you may have missed was the auto squaring, which took advantage of those extra limit switches I installed at the top of the Z actuators. To emphasize this process, I pressed down on this side of the gantry, and now you can see it's all skewed. Watch what happens when I home the Z. Each Z-axis motor does not stop turning until its corresponding limit switch is triggered, and all the limit switches are at the same height. Again, this gives us a nice starting point for further bed leveling. This auto squaring is also set up for the two motors on the Y-axis to keep the X-axis perpendicular. With that sorted out and the gantry as high as it can be, I'm going to remove the aluminum build plate and stick the Kinovo heater underneath it. To be completely honest, I'm becoming increasingly more worried about the thermal expansion and irregular growth of this single 4 foot by 4 foot aluminum panel. Your comments are not helping my fears. I want to point out that I'm not married to this idea, and if this plate turns into a taco, I am more than okay with moving off from this idea and going with a modular heating system. But since I have the massive heating pad, let's give it a go. Before I put the aluminum build plate back on, I'm going to install some plasma cut skirts to clean up the base of the printer and keep cold air out. While most of the printer is constructed from modular aluminum extrusion, the plasma cutter has been great for adding these customized components that clean everything up and make this build look a lot more professional. I can also finally attach the base to the frame with these machined right angle brackets. This should hopefully dampen that hollow vibration sound that you can hear when I move the Z-axes. Andy and I then reinstalled the aluminum plate and tightened each of the bed leveling bolts about 20 turns. I know that you hate it when I step on the build plate, but it's much more rigid now. I'm hoping that those 20 turns get us close to a flat surface, but to determine that, I need to sweep an indicator across the bed. My goal is to have the highest and lowest spots of the aluminum plate to be at most 1 millimeter apart. This amount of deviation would be unacceptable for a smaller 3D printer attempting to print at a layer height of 200 microns. But this printer is simply at a different scale. For prints that will take up the whole bed, I will be using a layer height of at least 2 millimeters, if not more. Anything less, and it would take weeks to print a large object. To fix the indicator to the pellet head, I milled this backplate, which will be used to not only hold the indicator temporarily, will also be used to fix the part cooling fan and bed leveling probe right behind the pellet head. Hitting that 1 millimeter bed levelness will come from both turning the bolts on the build plate as well as the gantry leveling. I will take an indicator measurement at several points now with the bed cool, adjust some of the bolts, and then take the same measurements with the bed hot. After measuring 9 evenly spaced points on the bed, I found that there was about a 1.7 millimeter difference between the highest and lowest points. Honestly, I was expecting way worse. After a couple rounds of adjustment, I was able to get it to under 150 microns. Next, I'm going to heat the bed up to 100°C. And wow, that took no time at all to reach the target temperature. Granted, that's only a 1/4 inch piece of aluminum that the Kinova pad has to heat, but still impressive. Just to confirm this temperature, I wanted to check it with my IR temperature sensor. The bare aluminum was too reflective, so I placed down a piece of anodized aluminum. The temperature reading of the anodized part is above 90°C. Okay, now I'm going to wait for a couple of hours, then come back and check the levelness. As I said, I'm worried about thermal expansion, but if I plug the bed length and the bed temperature of 100°C into a thermal expansion calculator, I'm getting 2 millimeters worth of growth. This is a little misleading because this is for a single dimension, and of course with the bed we have both X and Y. Also, 2 millimeters of growth directly in the X and Y direction would not be that bad, but all the bolts running through the plate prevent even growth. Instead, the bed will want to grow in the Z direction, creating a concave or convex surface, which is why I've been using the word taco to describe an undesirable bed shape. So at 100°C, the deviation is now about 400 microns between the tallest peak and the lowest valley. As much as I want to play a real-life game of the floor is lava as I try and adjust the levelness of the build plate when it's at 100°C, I think I'm going to have to pass. I'm fine with this amount of unevenness, especially since I'm going to use a glass build surface. I have to be real with you, the glass sheet is a gamble. I placed a custom order for 2 4x4 sheets at a cost of $1,000. If these 1/4 inch sheets break when I'm trying to remove a print from the bed, then this is just not going to work economically. Surely there are windows that are about this size that cost a fraction of the price. Well, the problem is that ordinary glass shatters at temperatures north of 70°C. Not good. The glass in this container is borosilicate glass, which you may know as Pyrex. This glass contains boron trioxide, which allows for a very low coefficient of thermal expansion. No expansion, no shattering at high temperatures. Let's hope though that the glass is not shattered in the box from transport. The glass plate is in one piece and it fits great. A little rudimentary, but I'm going to use binder clips to secure the glass to the bed. I also ordered some 12-inch wide polyamide tape for when printing with common plastics such as PLA and ABS. I'm hoping the tape will protect the glass from chipping when removing prints. That 12-inch width was a special order and has not arrived yet, but the weight is well worth it. It would be painful to lay down 2-inch strips across the 4-foot wide plate, or God forbid, 3/4 inch wide pieces of polyamide or Captain tape. As you can see in the background, I swapped out the white cloth that provided contrast to my logo with a neon orange acrylic sheet. Right now I'm using an external light bar to illuminate it, but I will wire some LED strips to provide some backlighting for prints in the future. With the glass build plate installed, we now have a surface to probe for quad gantry leveling. If this concept is foreign to you, then check out my Voron build videos. But put simply, we will use a mechanical switch on the print head to change the position of the Z actuator closest to the probe point to level the gantry. If the probe triggers early, the gantry is too close to the bed in that corner and the corresponding Z actuator needs to move up. I created my own version of Clicky, a Voron mod, for the mechanical probing of the glass build plate. My model is larger and accepts the high temperature limit switch, which I have used for all the axes on this printer. As you can see, during the quad gantry leveling process, the mechanical switch touches off on all 4 corners. After the 4th corner, the lead screws adjust to compensate for high and low spots. Here are the results after 3 passes. You can see that the completion of the first pass resulted in significant adjustments, with the largest being 0.496 millimeters on the back left actuator. This amount of adjustment is on par with the 0.4 millimeter deviation that we observed when sweeping the indicator on the heated bed. The adjustments needed decreased after the 2nd and 3rd passes, as the controller board found where to position the Z actuators for the most level gantry. I forgot to mention that I loosened the bolts running through the spherical plane bearings to prevent any tension from building up in the gantry. I will tighten those back down again. Next, I ran mesh leveling. During this process, the probe takes a measurement at 36 evenly spaced points on the bed and reports their heights. Here is the height map, and beneath it is the summary of the data. It looks like we have 0.25 millimeters worth of deviation. This may sound like quite a bit after the quad gantry leveling process, but I have 2 thoughts. First, as we can see from the height map, the deviation is mainly from the corners, and secondly, 0.25 millimeters is fine when you're printing at layer heights greater than 1 millimeter, which we will be doing. The standard nozzle size that comes on the MDPH2 extruder is 1.5 millimeters. When printing plastics such as PLA or TPU that benefit from direct cooling during the printing process, you need more airflow to cool the large diameter fiber that is extruded. For this reason, I selected a Delta blower fan, which has 28.3 cubic feet per minute of airflow. For a point of reference, that is almost 6 times more than the 40 millimeter fans commonly used for part cooling on filament printers. The blower fan mounts the back plate, but to get the airflow from the blower to the nozzle where the fiber is coming out, I created a custom fan shroud. Due to the weird shape and need for a hollow inside structure for airflow, this shroud needed to be printed by selective laser sintering. It was too large for the Sintertech printer, so I outsourced it to an online vendor. The shroud fits into the outlet of the blower fan, and I have some Z-axis adjustment to get the airflow as close to the printed plastic as possible without interference. There are a lot of small details that still need to be addressed. I've not set up the touch probe, configured the cabinet light, or relocated the emergency stop button to the front of the printer. But I have a level build plate, and I'm getting impatient, so let's fire up a print. With a printer this unique, there are a lot of parameters that need to be calibrated, such as the steps per millimeter of extruded plastic for the extruder, and all the different slicer settings. I gave my best educated guess for these values, but off camera I will have to print a known geometry, such as a calibration cube, to get these settings tuned in. The other problem I'm facing is that I have not set up a system for delivering pellets to the extruder. I have this fancy cardstock funnel that will need to be replenished with pellets every so often, but in the next video I will install this material conveyance unit sent to me by Massive Dimension, which will blow pellets from a reservoir to the extruder on demand. If you want to watch the installation of the pellet conveyor and see finely tuned prints, then definitely get subscribed to be notified when that video comes out. Finally, before starting the print, I want to thank this project's sponsors, OpenBuilds and Massive Dimension. OpenBuilds, of course, supplied all the components for the motion and the frame. The best way to support the Dr. D-Flo channel is to use my affiliate link below and purchase a CNC machine or components from OpenBuilds. The other sponsor, Massive Dimension, is a company looking to push the envelope of additive manufacturing. If you are interested in large format 3D printing, then definitely check out their product lines. If you think this extruder is big, then click the link in the description to see the MDPH10, which is capable of almost 6 kilograms or 13 pounds an hour of plastic extrusion. Okay, back to firing up the printer. For the model, I selected a vase. It's the quickest way to print a large object. I'm using Simplified 3D to create the G-code, and I'm using 3 perimeter layers, which will be more forgiving. I've uploaded the code, and now I can hit print. Honestly, this vase exceeds my expectation. It's 750 millimeters tall, and at its widest point, it's 350 millimeters in diameter. It took about 12 hours to print, and while it looks great, there were a couple problems that I noticed. First off, Simplified 3D did me dirty by including these irregular print lines just inside of the perimeter layers, even though I have turned off infill. Pellet extruders operate best when they are continuously printing, not stopping and starting, which would be the result of this geometry. Speaking of jerky motion, I did not tighten the lock nut enough on the x-axis. This resulted in a loose lead screw, and it had a strong tendency to whip. Finally, the last problem is that I need to increase the flow rate of the molten plastic out of the pellet extruder because you can see discrete globs of plastic were deposited, not a continuous stream. These are all manageable problems, and I will have them sorted out in the next video. And with that, I will leave you with some machining footage of the different components that I created for this video. Have a good one.